This was in one of the additional comments that you requested as well to solve Fourier transform in the context of an ODE. Right, so remember what is Fourier transform of a function? Fourier transform of a function is basically integrate the function from -infinity to infinity, right? So it's the area under the curve, except for you multiply that with minus jkx. Okay, so you modulate it with basically a plane wave over here, and but essentially it's like finding the area under the whole thing. Okay. Okay. So just to this Fourier transform obviously have lots of application. One of the application is solving ODEs. The concept is basically the ODE itself over here. As you see, it's a very complicated one. It's not one of the simple Euler type or constant coefficient, definitely not constant coefficient. It's not an Euler type. So we don't really have other techniques to solve it. The Fourier transform, the idea is you change every function of x. Right? So y of x, you change it to y of k. So you go from a function of x to y of k or y hat of k, and then solve it in the k space. Right? Sometimes we use this word in the k space. Solve it in the Fourier space, or and then it's usually much easier once you do this complicated thing, and then you just inverse transform it back. Okay, it's a little bit of work, but it immediately it's the only way to solve some of these equations. Okay, so the idea is you have a function and you can change it. So what you do is you apply a Fourier transform on that function. Right. So this is another notation for this. You apply a Fourier transform, and this is defined as you take whatever the function is here, multiply it, so modulate it with this phase factor, and integrate it from -infinity to infinity. So of course, this outcomes the x will disappear after the integral because it's a finite integral, and you're left with a variable k. So now you have a function of k like this. So just to differentiate from the original one, put a hat and just basically give this a name, right? Call it a function of k. All right. So how does this work? Right. So we'll do a Fourier transform on both sides. Okay, so you just apply the Fourier transform on both sides, and because if something is equal to something on before, you do the same thing to both sides, they have to equal, right? So if A equals to B, you try to square both sides. So A is B, right? So if you square both sides, of course they still equal. So if this side is 0, you do whatever to this side and do the same thing, they should be the same. Now, this is a linear operator because it's integral, which means you can do each term separately. Okay, so because of the nice properties of linearity, any constants can be pulled out. X is not a constant, so this has to stay in. And Fourier transform of 0 is 0, just from the definition. All right, so now we can worry about them term by term. All right, this one is actually the easiest. And I probably don't, I don't have time to justify this, but look back at your notes. If you Fourier transform a derivative, it spits out a jk. Right. Okay, so let's do this first. It spits out jk times the Fourier transform of that. So think of it this way. Right, so if you have d dx, it becomes jk times fy, right? The Fourier transform of y. This is two derivative, so it spits out a jk. It will be a Fourier transform of this, right? The y prime, and then you do it one more time because there's two derivatives, so it basically becomes this. Okay, and this one, it's x times y of x, and you need to look up again. So yeah, I won't have time to prove that, but what it will become is j times ddk of the transformed function. Okay, so again, this I remember because I use it a lot, but other ones probably don't remember. Put a mark in your notes so you can look it up very easily. Okay, so x times a function becomes a derivative in the k space times j. Okay, a derivative in the x space becomes k times the new function. So there's a nice symmetry. So if you ignore the j, right, x times the thing in x space becomes derivative in k space. The derivative in x space becomes k times the function in k space. It's a nice symmetry there. Okay, so now, yeah, this is y hat, this is y hat. So this just groups together nicely. Minus k squared plus jk times y hat plus 2j y hat dk. So you see the power of Fourier transform already. If I don't have the last term, I have, imagine I have a problem without the last term, just the first two terms, I have a differential equation. But after doing Fourier transforms, it becomes an algebraic equation, right? The last one makes it still a differential equation, however, it becomes a first order instead of a second order. And you know first order is always solvable, right? For most of, yeah. So that just becomes an exponential. Maybe I'll skip the algebra for that. Yeah, that's a separation of variables. So you should get y of k dot dot dot, right? You should get y of k is some constant times e to the k cubed over 3 plus or minus k squared over 2. Okay, are we done? No, we need to go back to the x space. So the k space is going from x to k is integrate everything times that. Going from k back to x, just change this to change the sign of that. Right? So minus infinity to infinity. So take the k function over here. Multiply by e to the, that was minus, so plus jkx dk. Almost, but whenever, because how the formulas work out, we go back, whenever you do any dk integral, you need to divide by 2 pi to make them work out. Again, I won't spend too much time to justify that, so you can put 1 over 2 pi here, or another way to remember where does the pi go is the 2 pi always goes with the dk. That's how I remember with Fourier transforms. Okay. So in case you forget, do I put a 2 pi for the forward transform or do I put a 2 pi for the inverse transform? Okay, yeah, so that's it. You can pull up the a, of course, you pull out 2 pi. Okay, any questions?